No. Oh my gosh. I better not say anything like shit. Shit. All right, guys. Any other questions as more people have come in? For section 8.3, how do you set up the distribution for 76? Oh, well, the funny thing is, I always hate how they place this kind of question. So you need to know you're going to make a confidence interval. So what distribution can you use? And by the way, do you guys notice, I'm pretty sure I said this, they don't use the little hats, they use this stupid little prime thing, but that should be p hat. We know better. That, of course, is p hat. It's not no p prime. That's bullshit. So which distribution should you use to create a confidence interval? I don't know. What do you guys think?
Normal.
Yeah, now, somebody else tell me, why are you allowed to use a normal distribution? You're good, Jan. You got your answer in there.
You check the P and the Q. See if the
Not
greater
P and Q,
than
you check. Not the P and Q. They can't be bigger than 1. It's N times P hat and N times Q hat. Does that sound familiar? It's got to be at least what?
5.
5. Does that sound familiar? So just like N greater than 30, we're very used to N greater than 30 by now. We are very used to that. NP and NQ greater equal to 5 is new, but it accomplishes the same thing. If I pass that test, that means I'm working with a normal distribution or normal enough. Is that all right, everybody? Some people are wondering the same thing. Does that make sense? Sure. Hold on. Let's do this problem. So in this problem, what's N?
100.
Oh, 1200, yes. What's P hat?
65%.
65%, so 0.65. What's Q hat?
0.35.
Good, the rest, I love it. So what's N times P hat would be 1200 times 0.65. Should be whatever the hell that is. 130 times 600. 130, 1.3 times 600. So what is that? 8. 780? Somebody save me. I'm trying to do it in my head.
That was
okay,
right.
So, all right, so 780, and then NQ hat would be 1200 times 0.35, and it's really just the rest, so it's going to be 420. 420. And then those are both at least what?
Greater than 5.
Yes. So this step works for percentage problems. It accomplishes the same thing that this step does for sample means. We're not dealing with sample means, so we can't use that. We have to use this check. NP hat and NQ hat have to be at least 5. Check normal enough for what? To do it. It is obvious. Do we have to write down the exact number we get, or can be just? Oh, yeah. Write down. You don't have to be exact. You don't have to write. Oh, I'm sorry. Oh, yeah. Thanks, Janik. I missed that question. Yeah, P and Q again. No matter what clothes they're wearing, they must add up to be 1. So if you know 1, you know the other one. Let me see. What was the other question? I like that. I need somebody. That's awesome. Anybody who sees a question in chat I miss, if you know the answer, go for it. Oh, yeah. So, I mean, you know, if you do n times p and you get 8,000.7649, just write in 8,000. I mean, I know what you mean. It's got to be bigger than or equal to 5. So if you get 8,000s, I mean, like, well, that's bigger than or equal to 5. I think that's what you mean. You don't have to be precise if it's crazy bigger than 5. All right. Anything else, guys? Nope. Okay. All right. So let me make this announcement. I figure since we haven't truly finished section 8.2 yet, we got into it last time. We talked about how to use the t-score chart, but we haven't really done example problems yet. I'm going to move the quiz to next Monday. The quiz is currently scheduled for this Wednesday. And if you look in Canvas, I've updated the due dates for 8.3 and 8.2 homework. So you have some time for that. So if there's no other questions, we're going to go right back into that handout we got into last time. Let me see. Where did I put you? There you are. My gosh. Oh, I'm so tired. Stop it. All right, let me share this bad boy. So we made it this far. If you weren't here last time, you picked a bad class to miss. We introduced a new chart, ye old t-score chart. So let's do a quick reminder about how to use this chart. So I pretty much always use this one for confidence intervals. So here's the idea behind it. If I want to be 98% confident, how much area is outside total in both tails?
2%.
2% in two tails. So how much is just in this tail, for example, just on one tail? If there's 2% outside here, how much is just on this side?
1%.
1%. I like it. In one tail. Now look right there. 1% in one tail, 2% in two tails. Of course, it's the same column. They both represent the same idea. So I pretty much always go here. So if I want a 95%, that's 5% outside. If I want a 90%, that's 10% outside. If I want a 99%, that's 1% outside, meaning in two tails. That's why it says two tails here. Don't these look like tails out here? Ship-up. I like it. Maybe. So let me erase some of this stuff. I got all kinds of stuff going on. Go away. Let's say I want to be 98% confident. I know I have a normal curve and I pick a sample of 28. What's my t-score going to be? Oh, and I don't know sigma. I only know S, right? That's the distinction. That's when I use a t-score, is when I only know S. So take a minute. Try to see what t-score I'm going to use. Of course, I'm like barely. Okay, good. I can move. So we know we're going to use this column here because I want to be 98% confident, and that's 2% outside. I'm going to use that column. And where do I stop? What's the degrees of freedom?
27.
27. So I'm going to go down until I get to 27. Then I'm going to stop. So that will be the t-score I would use. So either it's got to say it's normal or the sample size has to be big enough, as always. And that's for Z or T. So let me say this a few times. Why were t-scores invented? Oh, I can't write out there. Darn it. Why were t-scores invented in the first place? Anybody? It's for when I don't know something and I only know something else. What does it cover my ass for not knowing? Anybody remember?
The
Distribution
population standard
normal?
deviation.
Yeah, the distribution's got to be normal, but I use a t-score if I don't know sigma. So I got to have a normal curve. I like that. And then 2, I only know S. Jeff, do you spell? Not much. Not sigma. That's why it was invented. And just to remind you guys, let me erase all this. Go away. What are the formulas we know for confidence intervals so far? They are the first one we learned. And then I normally like to write the next one we're learning right now. And then, of course, we have the one we learned last time. This equation has a z in it, and that goes with sigma. This equation has a t in it, and that goes with s. The formulas are notes. You're not allowed to have notes, but you are allowed to have formulas. And some formulas are notes. Holy shit. Major loophole, Jeff. Oh, well, can't do anything about it. So when do I use a z-score? When I have a normal curve and I know sigma. When do I have to use a t-score? When I have a normal curve and I only know s. The formulas tell you that. Remember the t-score was to cover my ass? It's always going to be a little bit bigger than the z-score. If I have to use s instead of sigma, what does s mean? What is the symbol s?
Sample standard deviation.
All right. And now somebody else remind me what sigma mean.
Population standard deviation.
Good. So S is an estimate for sigma. So if I don't know sigma and I have to use an estimate, the t-score sort of covers my ass for that. And I like saying that not just because it makes you pay attention, because you don't hear teachers say cover your ass all the damn time, but also because it's exactly what it does. It makes it a little bit bigger because t-score will be a little bigger than the z-score would have been. It literally covers your ass for not knowing something. It's crazy. Literally. All right. All right, maybe. So let's try an actual problem. Wouldn't that be nice? Come on, Jeff. Enough with the concept. Give me a problem. All right, let's try an actual problem. Get out of here. This is going to be exciting. You're going to need your calculator, as always. Now, why do I say that? Because not only are you going to need it to do the formula, you're going to need it to do the data. I'm going to give you a bunch of data. So let's say I've got a normal distribution. This should be exciting. Let's see. So here's an example. We have a normal distribution. We take a sample of 7 data points, and we get these data points. You could do it, Jeff. Can I? Let me see. What is that? 1, 2, 3, 4, 5, 6. This is trying to be the number 13. And then we need one more, Jeff. We'll make it 9. That's exciting. So I know it's a normal distribution, thankfully, because if I didn't know that, why couldn't I do a damn thing?
N is less than 30.
N is less than 30. So this saves my ass to start with. It's normal already, so I don't care how big the sample is. And I want to create the 90% confidence interval for the true mean. True mu. So, fantastic question would be, what the shit, Jeff? So let's go through your thought process. I'm asking you for a confidence interval. So it's got to be one of these 3 equations up here. These are the 3 confidence interval equations. How do you know they are? They got freaking plus and minus in them, right? That makes an interval. So it's got to be one of those 3. So when do I not use those three intervals if I am not asking for a confidence interval? People use those formulas everywhere. It makes no sense to me. Only use them when I ask for a confidence interval. Are you guys with me? I don't know if it just drives me a little crazy to only use those if they're asking for confidence. I know it's not going to be the p hat one because I'm not talking about percentages. I'm talking about means. And I don't know sigma, so it can't be that one. It's got to be this middle dude. So let me rewrite this down here. So I've got to use this guy. Do I have N? Yes. Do I have S? So I know N, check. Do I know S? Do I? What is it? I don't know what it is. I love you guys so much. All I know is that I have 7 data points. That's N. And I know what the data points are. Do I know S? Do I know X bar? Not yet. What are you going to do to figure those out? How can you figure those out? I have a list of data. How can I figure out X bar and S in my calculator? This is one of the few things I'll let your calculator do for you because I put you through it in chapter 2. All right, I don't know if everybody is just shy today or if you really don't know. You put those in the list, right? And you do 1 var stats. Remember that? So we see, let me wake up my calculator. There you are. Calculator. All right, come over here, calculator. Come here. There you are. So let me do this with you. I'm going to stop sharing this page. Scheisse, where'd you people go? There you are. Let me share my calculator. Coolness. So now I'm going to go, I hit the stat button. So you hit, of course, you hit stat, edit. I'm going to clear this list over here, make some room, get out of there, clear you. And then just plug it in. So I don't know if you all wrote them down, but it's 11, 15, 7, 12, 13, 20, and 9. So what do I push to figure out the data, the analysis? What do I push to figure out the mean and the standard deviation?
Click stat again.
And then
Scroll over to calc.
calc. And then there's your
1 var stats.
1 variable stats. I like it. So let me get rid of this. I don't want a frequency list. Get out of there. Calculate, and I get my X bar, and I get my S. You guys doing okay out there? It's been a little bit of time since we did that, but it's going to come back now in a big way. So in this section, they can give me a sample of data because now I can do this stuff with just S. Now notice something. We've talked about this before. I'm almost certain. The calculator gives you S and sigma because the calculator is dumb. It is dumb. Now I feel like it's going to hurt me in the middle of the night. What'd you say about me? It's dumb. So it doesn't know if we just put in a population or a sample. We know it's a sample. Don't get all excited when you see this shit. We know we have to use this one because it's a sample we're putting in there. So we got to use this guy. Any questions about that on the calculator?
Can you show how to do it just one more time?
Sure.
Thank you.
So you got your data in the list, right? Then you go to stat, calc, I'm going to calculate something. I'm going to calculate my one variable statistics. Then you make sure the list of your data is there. I don't have a frequency list, so I leave that blank, and then I just hit calculate. And of course, if you have an older calculator, I think I'll just say 1 var stats, and you can hit enter because it defaults to list 1. Yeah, in fact, let me show you. I think it shows you. Yeah, it'll just say this. If you have an older calculator, you just hit enter, it'll do this. Is that okay?
Yeah, thank you.
You're welcome. So now let's come back to the sheet. Pop. All right, where did you go, sheet? Holy sheet. There it is. All right, I need my data now too. There we go. Let me see. So now I know X bar was 12.4. Let's go ahead and say 0.3 plus or minus. Oh, we still got to look up the t-score. We'll do that in a minute. Let me get all my other stuff in here. S was 4.237. That's what we just calculated, divided by square root of 7. So now we guys got to look up the t-scores. Everybody with me so far? Okay. Let me erase this business. What's the degrees of freedom to figure out this t-score?
6.
Yeah, so degrees of freedom is always n minus 1. And then somebody else tell me, oh, did I say? Yes, I did. I want a 90% confidence interval. So which column am I going to use?
4th.
Yeah, the 4th one, because that would 90% would have 10% outside on both sides. 90% would have a total of 10% out here in 2 tails. So now I'm going to use this. I'm going to stop at 6. Shaboo. 1.943. So instead of getting it from the z-score chart, I'm going to get it from the t-score chart. Right? I'm going to put it right in the same place, 1.943. So these are going to feel a lot like the problems in 8.1. It's just that instead of going to the z-score chart, I go to the t-score chart to get the thing that goes here. That's the only real difference. Let me erase this down here. I don't need you anywhere going. And now you just plug in the old calculator. Might as well show you that too. Gather. All right, I don't see any questions. I'm assuming everybody's completely cool with what I'm doing. Let me get my calculator up here. So in the old calculator, I'm going to do the error first. 1.943, 4.237 divided by the square root of 7. That should be everything, right? Yeah. Bam. So that's my error. It's my error. So I'm going to write that down here. You can't see it. Oh, well, I'm just putting it in to that page. I'll show you in a minute. 3.112. So now I can do 12.43 minus 3.112, and then I can do 12.43. No, plus 3.112. Bam! And I've created my interval. All right, let me stop sharing that. You guys doing all right on there? I know this is exciting. So I appreciate everybody's keeping it calm. I know this is insane. Holy shit, Jeff. So now I can write down, here's my interval, 9.32 up to 15.54. I can make the same decimal places as that. And then the last thing I need to do is write my conclusion. So we are 90% confident that what?
At the interval,
Yeah, 9.32. I didn't really give this any units, so oh well. So 15.54 contains the true
True of the population.
mean of the data. Yeah. So in a real problem, you would use units and you would use the true mean length of dolphins or the true mean radius of sprinkler water spray. I don't know, whatever the problem is. So the big difference between 8.2 and 8.1 is in 8.2, you're going to do more problems where you have to figure out stuff on your own. You have to put it into the calculator. And then instead of putting a z-score here, you just put a t-score there. That's really the only functional nuts and bolts difference to the formula itself. Just going to use the different chart. Are there z-scores on this t-score chart? Are there any z-scores
Yes.
on this t-score chart? Yes. Where are they?
At the bottom.
At the very bottom. I like it. I think somebody's chatting that at me. Yes, exactly. I like it. So I can use this even if I have to make a confidence interval where I know sigma. I just go, so if I stop, I get a t-score. If I go all the way down, I get a z-score. That's how this chart works. So I can use the t-score chart to get z-scores. That kicks ass. So what would the z-score have been that I would have put here instead? What would the z-score have been for 90%? Problem says confidence interval for 5M? What do you mean for 5M? Wait a minute. Oh, for true mean? True mean, not 5 means. Oh yeah, I know. Yeah, don't try to read it. Just try to listen to me when I say the word. Confidence interval for the true mu. That's okay. Don't worry. I understand. It's my horrible writing. I don't take it personal. I know all too well. You all should get a shirt saying I survived that horrible writing and all I got was this dumb shirt. And a passing grade is the hope. Okay. All right. How you guys feel about that? Do you feel okay about that? You feel shitty about that? You feel...
Just a quick question. So when we're looking at the t-score chart, like, so for the problem that we just did, we were looking at 90% confidence interval, right?
Yes.
So when we look at the t-score chart, can you explain which words are failing me right now? I'm sorry.
So how did I know to look at this column?
Yes.
All right. So because it actually is kind of cool. It's harder to mess this up because either way you look at it, it's both the same column. So if I have a 90% confidence interval, what total is out here? If there's 90% in here, what total is out here?
10% outside.
10% in two tails. How much is in one tail then? How much is just in this side?
0.5.
0.5. So
Oh, yeah.
5% in one tail. See, either way you look at it, you're in the same column. Now, in the next chapter, it's going to really make a lot more sense why we have these two rows. We're going to have certain tests that are one-tail tests and certain tests that are two-tail tests. And you just go to the right place. That's all. All right. Now, how's everybody else? All right. I'm going to take that as a good thing. So let's look back. If I do this, can you see the t-score practice chart page? I mean, whatever. Help your old teacher out. Can you guys see the t-score practice?
Yes.
Okay, thank you. So go ahead and do the second one. I talked a little bit about this second problem last time. So, all right. If I have an 80% confidence intervals, real quick, guys. If I have an 80% confidence interval, can you see the two tails I just made? Just to make sure everybody really understands what I'm talking. Aren't these two tails here? Do you see why we call them a tail? It looks like a freaking tail, right? On both sides. If there's 80% in here, what percent is out in the two tails? Obviously, it's 20%. Is that cool? So 20% in two tails is the same thing as, well, what's in this part then? 10%. So 20% in two tails is the same thing as 10% in one tail. So on the chart, in that problem, I would look over here. 20% in two tails, 10% in one tail. They both end up in the same column. How's that? Is that all right? Let's see. Okay, okay. So if you remember last time, we actually identified the one that can't be done. You could do all of them except one in number 2. Oh my goodness. All right, let's see.
Did you stop recording?
Huh?
Did you stop recording? Are you
Did
still?
I?
I don't think so.
I'm still recording, yeah, because I'm going to come here in a minute. So I
Ah.
didn't see a reason to stop. Yeah.
Oh, yeah.
I know this is going to be a really exciting part of the video, but people will get over it. Let me see if everybody's catching on here. So part A. Is it okay that n is less than 30? Is that okay?
No,
Yes.
Yeah.
Yes.
no.
Totally is. Why is it completely fine that n is less than 30? Because
It says it's normal.
it's already normal. It doesn't need to be saved. So if I have a normal population, if I take a nice random sample from it, all the sample means will still be normally distributed. So I only need an n greater than 30 if I don't know what the population distribution look like, if I don't know it's normal. So that's check. Number 1, to be able to do shit, I need a normal curve. Now, how do I know, do I use T or Z?
If it has a sample population or sample standard deviation.
Cool. And of course, here I see I have a, yeah, so sigma is known. So therefore I can use, holy crap, Jeff, I could use a dictionary. Sigma is known. I could use somebody else to write for me. All right. Let me just put sigma check. There we go. So I can use what? What kind of score? normal. I know
A
sigma.
Z-score?
Now I can use the Z-score. I love it. So now let me show you. I would use the T-score chart. 90% confident, which means 10% outside. So I'm going to use this column here. And if I go all the way to the bottom, 1.6 for 5, that's the Z-score. So if I go to the bottom, I get a Z-score. If I stop at some degree of freedom, I get a T-score. Is everybody with me on that?
Can you explain that one more time?
So remember, the reason T-scores exist is to cover me for the fact that I don't know something. So the larger my sample gets, the more certain I am about S approximating sigma. So the whole reason T-scores were invented, if I don't know sigma, I have to use an approximation, S. When does S get better as an approximation? When the sample gets bigger. So as my sample gets bigger, my T-scores I need get smaller. I need to cover my ass less and less. So when the sample size gets large enough, I don't need a T-score anymore. I can just use Z-scores. I don't need any extra towel to cover my ass, right? Okay, I like it. I want to make the T-score towel to cover your ass. All right. So that's that one. Oh. Are we solving the problem? Well, there's no problem to solve. I'm not your problem to solve. Sorry. There's no problem to solve. The whole point is just to find the appropriate score. So we did it. I don't know X bar. I can't make a confidence interval. Are you guys with me? I don't have enough information to actually make a confidence interval. That's fine. Yeah, this section is really just focusing on, do you know how to use the T-score chart? And do you know when to look where? T, Z. So in part B, why is it okay that the population is not normal?
N is greater than 30.
Good, got a good sample size. Good, so that's the first thing, check. So now is it T or Z? TORS.
T.
T.
Yep. Why is it T? Because I only know,
The sample.
good, the sample standard deviation. So I have to use a T-score. So what are my degrees of freedom going to be?
38.
Good, one less than the sample size always. So degrees of freedom is 38. I got a 98% confidence level, which means how much is in two tails?
2.
02, I like it. So this tells me what column to look at, and this tells me what row to stop at. So I want the 2% column, which is this one. And I want to stop at, I've forgotten, 38. So I want to stop right at 38. Looks like 2.429. You guys see that? All right. So my T-score is 2.429. So what is it that tells me to use a T-score if I don't know sigma, but I do have a normal distribution? I have to have a normal curve to do anything. So of course, look at part C. Does my sample size save me? No. Does my population save me? No. So I am unsaved. So I cannot do this problem. Not doable. Can't be done. Leave me alone. All right, so go ahead and do part D if you haven't finished that. So part D ends up being like doubly good, right? Sample size ready to save us, but the population's already normal. Check, check. Z or T?
T.
T, because I only know S. I don't know sigma. What's my degrees of freedom?
60.
60. I like it. Always one less than N. And I really need to introduce this symbol. I haven't introduced this symbol yet, and that's my mistake. And I'm thinking about this right now. There's a little symbol. Let me ask you, for 99%, what area is in the tails? What area is out here? Don't worry, I'm going to get to the symbol here right now. It's going to represent the area in the tails. What area is out there?
1%.
I heard somebody, I think, yeah, 1%. So here's the symbol for the area in the tail or tails. It is the Greek letter for A because it's area. Crazy. We're very creative people, us math people. So alpha is the Greek symbol for A. It looks like a fish, which is great because it's talking about the area in the tail. So you got fish tails. Fantastic. So that alpha would just be the area in the tails, 0.01. I just want to introduce that symbol. You might have seen that symbol before in the book already, but nobody's asked me about it. So the little alpha dude is the Greek letter A. It just represents the area in the tail or tails. So what would alpha divided by 2 be in this case? I got a skinny little fish here now.
0.005.
0.005, and that would be the area in one tail. All right, so if I look at my t-score chart, degrees of freedom is 60, and I got a 0.01 in two tails. That'll be this first column. See, there's the 0.005. That's the alpha over 2 there. But I can look at this one directly. 99% means 1% in two tails. And then I'm going to stop at 60. 2.660. All right, so if you got 2.660, kick ass. All right. So you got to know how to use the chart. You got to know when to use the chart to get a t-score. And you have to know when to use the chart to get a z-score. So try number 3. I'll stop recording this time. This might take you a little bit. By giving you this formula, but we know it's going to be a t-score. I mean, that's the whole purpose of this little sheet is all about t-scores, but why exactly do I have to use a t-score?
We only know S.
Yeah, and why am I allowed to do anything?
Normal.
Good, it tells me it's normal. So it doesn't matter the sample size is only 7, because I already know it's normal. All right, so those two work together. Got to know it's normal to do anything. And then S means I have to use a t-score. Sigma, if I know that, I'm allowed to use a z-score. So now, to figure out the t-score, I need my degrees of freedom, which is 6. And what's alpha in this problem? Let's start using that symbol. Got to check. Let's see. No, it's not. Be careful. That would be alpha over
102.
2.
0.4.
2. 98% means there's 2% in the tails. Is that cool, everybody? Alpha means the area in the tails. In the future, it could mean in one tail if I have a one-tail test, but a confidence interval pretty much always makes 2 tails. So if we look at the t-score chart, 0.02 is this column. I stop at 6. Looks like 3.143. that what it was? I forgot already. Yes. And then I just plug everything in the old formula and see what comes out. So I get 78.29, give or take 18.679. How are you guys doing? Is that what you guys get?
That's what I got.
Okay. I don't know if you guys notice this. That's a pretty big error. But of course, it makes sense. I got such a small sample size, and I had to use a t-score, which makes the error even bigger. Oh, Jeff, you still need a calculator, dude. Do it in my head. I don't want to. Okay. So 78.29 minus that. It's 78.29 plus that. Now, considering what the problem is about, it's about grades. I haven't written the conclusion yet, I know, but I just want to point something out. Is this a very useful interval? It goes all the way from failing to almost A+. So it's not, so if it was sort of like, what do you expect you're going to make in this class? Anywhere from a 59 to a 97. Okay, so you don't know shit. That's what I'm saying. So that confidence interval sucks. But why did we expect that? Because we have such a small sample. And we want to be 98 freaking % confident. So it's going to go even wider out. So in this case, I probably want to take a larger sample. Because otherwise my confidence interval doesn't mean shit. Well, what does it mean? It means we are, where'd it go? 98% confident that the interval become of the 59.61 to 96.97 contains the true mean grade. Ruh-roh. So small samples, well, small samples have a much more likely, or they're much more likely to end up with a large error. Yes, so small samples, will they always make a large error? No, they won't. Nope, not necessarily. But we knew on day one, is it better to have a bigger sample or a smaller sample? We knew on day one, it's better to have a bigger sample. I mean, if this data, if this stuff right here, these numbers were based on a sample of size 70, I would put a 70 here, and that would make this much smaller. You guys, are you with me? There are several homework problems that basically ask you that same question. And my error would actually become 5.9. That would be a much better interval. That would actually mean something more to me. But right now it goes everywhere from an F to an A. That's not very useful. Okay, good. So I don't want to make it seem as if small samples always equal sucky intervals. No, that's not true. but they definitely make it more likely that I will have a sucky interval. That's why we always try to take as big a sample as is feasible, or as is within our means of resources. Yeah. So most online stuff that takes surveys, they take surveys somewhere between 1,000 and 1,800, somewhere in there. They survey that many people. Because it normally ends up being like a 3% error, which we can live with. That's fine. I can live with that. But if I had a 20% error, I'm not even going to put that anywhere. I'm not going to tell anybody about that. All right, maybe. I had this whole thing over here. I don't really want to do this right now, but this works so much better in the classroom because then I can have people walking around and checking stuff out. I would have like average grades for women and average grades for men. So I'd have little groups of women and little groups of men working on this, and then they can kind of compare answers with each other and see who seems to be doing better. Anyway, I'm not going to worry about that right now. All right. So any last questions on T-score related stuff? Do you want to do it? We can do it. I mean, I have one person privately chatting me that they're all upset we're not going to do this. It doesn't take much to make me.
No, that's okay.
All right. So we're not going to do it. Don't worry. It is interesting because the one thing we miss out on, let me see if you guys remember. If I am making 90% confidence intervals, what percent of the confidence, if each of you made your own interval, what percentage of the intervals that you guys make would not contain the real mean? You could do it.
10%.
10%. We're 90% confident, which means if a bunch of intervals were made based on some other people's sample, everybody's going to pick different numbers, then I would expect about 10% of them to not contain the real mean. And this number down here is the real mean. So what I would do is I would say, put your intervals on the board, and then I would step back and see how many didn't have the mean in there. And most of the time, if I had 20 groups, then about 10%, would not be containing the real mean. It's kind of cool to see, but it's not easy to recreate here. Okay, let me stop sharing for a moment and kind of reset myself. All right, any questions? We're about to leave chapter 8 behind, and we're going to go a little bit in chapter 9. I think we're going to let us out a little bit early, just because. But we are going to get a little bit into chapter 9. Any leftover questions? No, okay, all right. So let's do this. Get a little drink. Let's see. So what we're about to get into is how to test claims. And this is the big thing that statistics is known for. You always have those commercials that say 4 out of 5 dentists say this or whatever. That might not be a bad example to do. Well, no, not to start with. Okay. So if, for example, these are used for things like drug testing. You have a claim that you make. If I make a new drug, it's going to replace Tylenol. And I say, oh, my new drug cures headaches faster than Tylenol did. Then I can do a little study. I can have people, I can have them sign up for little studies. they can get paid for it. I give some a placebo and I give some the real drug. And then I try to see, do I see that my drug on average acts faster? Right? So that's the idea. So we need to get used to the structure of setting these things up. In the real world, you're not going to use every step we're about to do. The steps are important, though, to keep us understanding the idea behind this whole process. All right. So let's come up with, let's say that somebody claims, yeah. So let's say I don't know why I always go to this example. I go to the lumber yard and I see a stack of boards that have already been cut, right? They cut these boards, and this is old school lumberyard. This is people doing this by hand, right? They don't have these big old machines doing this, so it might not be as perfect, right? And I want to buy a stack of wood, and they tell me that, oh yeah, the average length of all of our pieces, they say the average length of all their pieces is, I don't know, doesn't matter, Jeff, 5 feet. So that's a claim that they've made. They claim that their average is 5 feet. So if I'm going to test that claim, I'm going to try to show what? If I want to test that claim, I want to see if I can show what? Well, I might be a little too open-ended. Let me try it this way. If that's the claim, the mean is 5, what would somebody think who doubts that?
The mean isn't 5.
Beautiful. I love it. Okay. So I always think about this. Remember back in the day when we used to go to this place? Well, you know the place still, Starbucks. Some of you guys might, but we used to actually go there and sit down inside. And we would see little old people. I always see a group of little old people. I'm like that. I'm very quickly approaching that. And very often they have very opinionated conversations. So I kind of love to sit near them. Sometimes you're like, oh, that's enough of that shit. I got to get away. So I always think about this as 2 little old men in a coffee shop. One has an idea. Let me not go there too yet. So one guy thinks the mean is 5, and the other guy basically always thinks he's wrong. So he's going to think the mean is not 5. So there's the first step in any of these kind of things, in any of these claim testing problems, is to figure out what the claim is, and then what is the opposite of the claim. What are the 2 sides of the story here? So either the mean is 5 or the mean isn't 5. Those are the 2 possibilities. That doesn't seem too hard yet, right? What if my claim was the mean is greater than 7? What's the opposite of that?
Less than 7.
It's not less than 7. You might have said it. I can't hear you.
Less than or equal to.
Yes, less than or equal to. All right. I like it. And you can keep going, blah, blah, blah. Doesn't matter. So there's always going to be a claim and the opposite of the claim. So that covers everything that could possibly be true. Either it is 5 or it isn't 5. I like it. Now tell me this. How do I say this? Oh, that's fine, Jeff. I won't go there yet. I'm not going to look at all of his lumber because there's a ton of it. It's just everywhere, right? So I'm going to take a sample. I'm going to randomly sample. So I'm going to walk around and I'm going to dig through and I got some people helping me out. We're going to randomly sample a bunch of these pieces of wood, right? And then obviously we're going to take a mean. If the sample, let's say I take a sample of 32 pieces of wood, right? And I get a sample mean of 4.92. Stay with me. Is everybody with me? So this dude claimed that the average of all of his wood pieces was 5 feet long. If I take a random sample and I get a mean of 4.92, a sample mean of 4.92, do I stop there and say he was wrong? Why can't I just stop and say he's wrong? 4.92 is less than 5. It ain't 5. But I can't say he's wrong. Why not?
Because it's with air.
Yeah, there's good. I love it. So coming right off of our last chapter about confidence intervals, I don't know what the error might be, but more importantly, I can only disprove him if I look at every single piece of wood, right? I can only disprove him directly if I look at every single piece of wood, because maybe I just happened to pick a bunch of them that were smaller, right? And if I would have just picked some more, maybe I would have gone up. Is everybody, I cannot prove something without looking at all of it. I can't use a sample to prove something equals something. I can use a sample to show evidence that it doesn't equal something. So I like what somebody just said about the error, but it actually is not really exactly the error from confidence intervals. It deals with the standard deviation. All right. So I'm getting a little ahead of myself. But the whole idea is, if this person is right, any sample mean should be close to 5. So is this close to 5? Let me ask you that question. Let's see if you guys remember about this question. Is that close to 5? I love this question.
Depends on the standard deviation.
Exactly. I love it. That is the right answer. It depends. I have no freaking idea. If the standard deviation I'm using was 1 foot, that is way close. That is monster close. That's not nowhere near a full standard. But what if the standard deviation I'm using is 0.01? Then that's 8 standard deviations away. Holy shit, that's forever away. So don't say, yeah, 492 is right next to 5. You don't know. You don't know. That could be 4.92, light years. And 5 light years, so it's a lot farther away. All right, sorry. All right, I like it. Maybe. So let's come back to this. So that's the idea. We're eventually going to get to there. But this is step 1, is to deal with, what are my hypotheses? What statements am I working with? What's the claim and what's the counter to that? What's the opposite of that? So we have a hypothesis called the Null Hypothesis. Oh shit, just a word, H with a little O on it. So yes, I will refer to it as the HO. And then you have the alternate hypothesis, which is the opposite of this one. And it's an H with a little 1 on it. So I will call this the high. So we have the HOs and the highs. I like it. Is that the technical name for it? No. It's just a quick way to reference those things. Okay. One other little thing I want to point out right now is that this guy, and by the way, I do have a handout for this, and it goes over all this stuff just so you can have it to reference as you do work. This guy always needs an equal sign, be it equals or greater than or equal to or less than or equal to. Those are the things that this guy, H naught, or the HO, needs those symbols and needs to have an equal sign of some kind. This guy would then have the opposite, not equal to, greater than, less than, something that does not have an equal sign in it. Now, let me see if you guys get this. If I think this guy is wrong, if I think his claim is wrong, how could I show that using a sample? How could I show evidence that his claim is wrong using a sample? So he says the mean is 5. How could I show evidence that he's wrong? I have got to be, all right, let me see. Didn't we just say that if I'm somewhere close, then that's probably okay? And we still have to define what close is. It's going to be related to the z-score, of course, right? We know enough now that we know z-score is all about distance. Are you guys with me? So if my sample is somehow close, which you haven't defined yet for this problem, but in general, it has to be, if it's close, I can't say he's wrong. So the whole idea then is the sample I take must be far away. Does that make sense? If he says I claim is 5 and my sample is like 3 standard deviations below that, I'm like, you're full of shit. You're completely wrong, my friend. I'm sorry. That would be evidence that the claim was wrong. We already established earlier, you guys did, that if it's close, it's okay. Therefore, when is it not okay? When it's far, when it's far away. And we've already talked about this in this term. Where did unusual start for us? Where does unusual start in the problems we've done before?
More than
After
2.
2 standard deviations.
2 standard deviations away. Wouldn't anything outside of there be evidence of weirdness? Because that's where unusual starts. So now in this chapter, we're going to be more specific about where unusual starts. It depends on the situation. So, for example, if I work in a nuclear power plant, I don't know if I've given this example before to you guys, and I got that little needle that goes green and then it goes yellow and goes red. Am I going to just sit on my ass as it goes from green and starts to approach yellow? Am I just going to sit there like, oh, wait, we'll see if it hits red? Or am I going to get off my ass and go, let's get on that right now? I'm probably going to get off my ass. So I'm not going to say unusual is 2 steps away. I might say unusual is 1 step away. I don't want it to get very far away from normal operations. Are you guys semi with me? Maybe. In some other situation, it might not be that crucial, right? I don't know. Off the top of my head, I can't think of anything. Oh well. But that's a situation where I want to define unusual as something not that far away because I don't want to let it get close to blowing up, right? All right, maybe. Okay. So that is the idea behind this whole thing. So in this case, do you see how this is a not equal to? Which means I could either be down here or up there. So if we walk around and we get a sample mean of 6, that might be enough to say that's wrong because I'm so far away. Or if I get a sample mean of 4, that might be enough to say it's wrong because I'm so far away. It depends on what the standard deviation is, like somebody pointed out. But still, I have a 2-tail test because I can go either way to show that this is wrong, to show that this guy looks right. Not equal to means bigger or less. So this would be a 2-tail test. So when would it be a 1-tail test? If this said greater than or less than, because that would be specifically one direction or the other. Let me stop for a minute. I'm going to let you absorb this. By the way, just so you know, this is step 1. There are 5 total steps. When I was taught this, there were 8 steps. So I cut 3 steps off. You're welcome. You probably, that probably doesn't excite you that much. There's still 4 more steps to go through. So of course, as we learn it, it's going to take a while. The actual doing of them, once we know them, won't be that long. All right, so this is step 1. It's all about setting up the null hypothesis and the alternate hypothesis which are basically just two old men in a coffee shop who disagree with each other. They're opposites of each other. All right. So let's do so this is step one, but I want to focus on step one for a bit. Let's do another example and set up step one. Okay. So say I claim that my drug alleviates headaches caused by listening to me. Let's see, quicker than 10 minutes. So what is my claim in Mathish? I can see it in English. What is my claim in Mathish?
Would be less than 10.
Yeah, my claim is my mean time to have headaches alleviated is less than 10 minutes. Now let's see who is paying attention. Where will that go? Which one of these guys thinks this? Who's allowed to have just this symbol?
Hi.
Hi.
Alternate hypotheses.
That's right. I like it. It felt like everybody was saying hello to me. Hello. All right. So it is the high. I like it. So which means the other dude is going to think what?
Mu equals 10.
No.
Equal to or greater than 10.
Greater equal to. I like it. Now, you will see in the book, every now and again, they'll just have an equal sign here. I try to teach that it should always be the opposite. Sometimes they'll say it's okay to have an equal sign there. And I understand that idea, but it just makes more sense in general to say that these two are opposites of each other. Can you tell me then, how can I show evidence? So here's the next thing I want to point out. This is what I can always show evidence for. I want to really make this make sense. If I take a sample, if I give my drug to a sample of people and I get X bar equals 10 minutes, I get a sample mean of 10 minutes, does that prove that the mean is 10? That the real mean of the drug is 10 for everybody? I want you, we know this. I can never prove equality using a sample, ever, ever, ever. Because almost for sure, whatever the mean of a sample is, the real mean is something different. But I can show evidence that it doesn't equal something. So if somebody's like, the average age of Grossman is 70, and we're like, okay, you're insane. Let's look at a sample of students, and the average is 24. You're completely wrong. I don't even need to worry about the standard deviation. You're completely insane, right? Okay, maybe. So I can use a sample to show it evidence that it doesn't equal something, but I can never use a sample to prove that it's equal to something. All right, maybe. Is everybody still with me? This is some weird shit, I know. And it's not the most exciting stuff, I'm sorry. All right, maybe you're still with me. So this is the guy that's always going to set up where I can find evidence against this guy. So if I want to show evidence that it's less than 10, oh, that's different. Okay. If I want to show evidence that is less than 10, where would my sample have to show up to show evidence for that?
On the left.
Which side? Oh, I gave it away. It'd have to be down here. If I got a sample here, I got a sample right there, that far away, that would be evidence that it's less than 10. So this would be a one-tailed test. So this is what I told you was going to happen. Does either side work now? No, because I'm trying to show it's less than. So if I got a sample up here, that does nothing for me. Get out of there. Thanks. I don't need you. Only one side will show evidence that it's less than 10. That's this side. So this would be a one-tail test. So when I go to look at the t-score chart, I have to look at the one-tail test row. Okay. So I told you this was going to happen. To really explain why this t-score chart has a 1 and 2 tail, these guys are 1 or 2 tail tests. Funkadelic. So let me do this. Let me see. Yeah, let's do that. I'm going to do one last thing with you today, and then we'll call it a day. I want to just show you this, and then I haven't posted it yet. And now we all have to patiently wait for me to discover it again. Shit. Hold on. Give me. Oh, shit. I almost closed the whole meeting. That's good, Jeff. Let's see. Do. Where are you? Here you are. Okay, I have found it. Well, good job, Jeff. All right, be quiet. So I'm going to post this up on Canvas. And we are going to still talk about every step. But I just want to show you this. All right. We can do the first part of this. So take a minute and read that problem. I'll be right back. I got to get something out here. Gosh, get about 7 political ads every day. I've already voted, people. Can't I just get that out there? I've already voted. Stop telling me who to vote for. Can you guys identify what the claim somebody is making in this problem? In English. It was very nice in this problem. I bolded it.
That coyotes that are in captivity that are given more room live longer than 10.5 years.
Good. Yeah. And 10.15 is the normal life for coyotes in captivity. So my claim in Mathish is the mean is greater than 10.15. Do you guys see how that goes together? So you can see it in English. Coyotes live longer if they're given more room to roam. Live longer than what? Normal. So the claim is the mean is greater than 10.15. What is this number here? Where'd that number come from? That's a mean, isn't it? But where'd it come from? That's the sample mean. The sample mean is never going to show up in my claim. Because in real life, I would make a claim and then I would go take a sample. So the sample stuff will never show up in this first step. Now, somebody else tell me, which one does that go into? That statement we just wrote here.
Alternate hypotheses.
Yes, in the alternate hypothesis, the high. Because it's got an equal, because it doesn't have an equal sign. And then the opposite of that is going to be
less than or equal to.
I like it. I like it. So is this going to be a one-tail test or a two-tail test?
One tail?
Yes, it's going to be a one-tail because this guy only allows for one direction, not the band. Right, so the only way I can show evidence for this guy is to find a mean up here somewhere. That's one tail. This tail doesn't do shit for me. That would not show evidence of greater than. It's only up here. Does that idea Makes sense. Step B is a step we know already. So I'm not going to talk too much about part B, but can somebody see what tells me if I can use Z or T scores? Or maybe nothing? What two things do I need? In fact, I kind of explained it to you here, but try not to read that. We already know this. Z or T. So what two things do I need to know? The most important thing I need to know is, am I working with a
Normal.
full deck? I mean, a normal curve. How do I know this is a normal distribution I'm working with?
We have a sample size bigger than 30.
Yeah. N is 41, bigger than 30. It's normal. Now I can figure out, is it Z or T? I know it's not nothing. I can do something. Is it Z or T?
Z.
Huh? Sorry?
Z.
Yeah, why Z?
Because we know the population standard deviation.
Yes, I know the population standard deviation. And again, I was very, very nice. I not only bolded it, I made it blue. So sigma known. Therefore, I can use Z source, Jeff? Really? Really, 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 really? Yes, Jeff, really. Okay, Z scores. All right. I think that's enough for today because now I need to talk. Part C is where part C is where this kind of thing happens that I was talking about, defining what far enough away is. This is not that big of a deal really, but I just want to give us time. And then part D is where all the work happens. And then of course, the last thing we have to do is write a conclusion. Yeah. You know that's coming. That's a huge part of statistics is, okay, you got numbers. That's good for you. What did those numbers mean? Right? All right. But I think that's plenty. I think we're going to call it. That's a lot for today. These are kind of weird. So I have given us a few days to talk about these in the class. I just said that. I'm sorry, Frida. Yeah, I'm going to upload it right now. As soon as I log out, I'll upload this sheet, maybe without all this writing on it. Cool. So I will put it, it's not up there yet. I'll put it up there right now. All right. So let me know if you need to stay, if you have any questions. If not, let me see. You're welcome. If not, I'll go ahead and start putting this up here. Everybody okay? You guys have any questions? Okay. All right. Let me see. Oh yeah, practice quiz. Yes, I almost forgot. So I will post a practice quiz and then I'll try to get the solutions maybe over the weekend or before that sometime. Yeah. I am planning on a practice quiz, yes. All right, guys, I'm going to head out. I don't hear anything, so I am out of here. Bye, everybody.